Imagine there's an immense social movement. Crowds leave their homes and take to the streets. And there you could be, trying to join other protesters to demonstrate in the streets and defend your ideals. So, consider the following scenario. Protesters are now scattered throughout the city and they all share the common objective to gather into large enough groups to perform significant actions. They face counter-forces that may break up groups, block some places or streets, and seize any communication device protesters may be carrying. As a consequence, protesters only have access to local information on people and streets around them. Furthermore, formed protesters groups must keep moving to avoid containment by adversary forces. This situation is not imaginary. It describes events that took place during the Arab Spring or the social movement in Hong Kong. In this scenario, protesters need a distributed and as simple as possible protocol that utilizes local information exclusively and ensures the rapid formation of significantly large, mobile and robust groups. This is what I will call in this presentation a flocking behavior. In a previous work, we proposed a set of rules to enable such behavior on networks. In this presentation, after modeling our framework, I will recall how these rules work. Then I will present a new contribution. By considering vision, which is the fact that walkers can see further than their next location, we greatly improved the flocking behavior. So, let's dive in. The first thing we need is a framework to simulate displacement of protesters in a city. We model cities as undirected graphs that we call street networks. On the other end, protesters are biased random walkers on this network. They can move from node to node with simple rules. We will get to those very soon. So, in order to model real-world cities, I'll leverage OpenStreetMap database. For a given city, I extract the undirected graph defined as the node that represents street intersection in the street and the link between those nodes that represent pieces of streets. I use a typical instance, namely Paris, to present our work. Indeed, our result did not differ much from one city to another. One last thing, the links of a street network generally represent street segments of very heterogeneous length. Then moves from a node to another may have very different duration. In order to model this, we split each link of the street network into pieces connected by evenly spaced nodes, so that all walkers move have equal length. That procedure is illustrated on the figure. Let's go back to the protesters. Given a city network, we model them as a set of biased random walkers. At each time step, a walker moves to a new node among its neighbors, and the walker can use two criteria to determine its next location. One, there's the number of walkers located at this new node. The second is the net flux of walkers on a link. This is, at given time steps, the difference between the number of walkers that enter the link from a node and the number that entered from the other side. We now can clearly describe rules for the movement of walkers. The first one is the attraction rule. A walker moves to its neighbor that maximizes the number of walkers. And the second is the alignment rule. A walker moves to its neighbor that maximizes the net flux. Those are the best and most important rules we found in our previous work. And so far, those rules did not take into account the vision of walkers. This means walkers chose a new location using only information on neighbor links and nodes. We now present the vision-based rules that consider the depth of the vision of walkers. We construct walkers' vision in the following manner. We introduce the concepts of vision depth and branches to define how a walker combines the rules from the previous work with a wider field of vision. A walker can see what happens on the network up to a certain distance from its location, which is the vision depth D. Notice the depth of a walker vision can differ from one criterion to another. Within this field of vision, a walker can look into different directions, at least one per neighbor knows. We say a walker perceives multiple branches. This is a central contribution of our work, all done tight. It may look complicated, but the image will help a lot. Basically, a branch B is a simple path, a sequence of different nodes that form a path from the location of a walker. As you can see on the figure, the walker on node U with a vision D equals to 2 has access to the information on the sequences of link and nodes highlighted by arrows, as they are the two first nodes and links on the branches starting from U. Now what matters is that a walker uses the criteria we previously defined with a wider range of vision to choose how to move. So now we aggregate those criteria, taking into account that the walker now sees multiple values for each criterion in the following manner, displayed on the screen and detailed in the article. A branch is then weighted by this quantity. Finally, for a walker to follow a tactic defined by a pair of vision depth, one for each criterion, is to identify the branch B with the maximum weight and subsequently moves to the neighbor at the start of this branch. Great. With that network framework and this new walker model of ours, we can tackle our experiments. As I said, we want walkers to be flocking. We characterize it as a gathering of walkers that still keep on exploring the network. In our previous work, we showed that big enough groups of walkers only form with rules that also make walkers explore the network. Therefore, the gathering of walkers is on its own a good indicator of the efficiency of our model. We define it as the average size of non-empty groups of walkers and use the metric to evaluate the efficiency of our work. We seek to understand how the vision depth impacts walkers' dynamics and if this new feature improves flocking. We run all experiments on the discretized Paris street networks with as many walkers as there are nodes in the network. They all start at random location. To understand the impact of the vision depth or walker behavior, we first measure the impact of the vision depth on the gathering score obtained at the end of a run for each criterion. As you can see on the figure, for the attraction rule, the orange line, the gathering score on the y-axis linearly increases with the vision depth on the x-axis. This is because walkers can see further and therefore interact with a number of walkers that is proportional to their vision depth. The gathering score is then roughly 2 times the vision depth, as a walker in a street sees exactly twice as many nodes as its vision depth. More interestingly are the results for the alignment rule. In our previous work, we showed that each rule taken separately, the alignment rule is the best, except that it cannot prevent a group of walkers from splitting into 2 groups at intersections. However, with a vision range of 2, when a group of walkers split at an intersection, the walkers that form the smallest new group They can see and perceive a positive net flux from the other workers. They therefore are capable of coming back and following their original group. This means that given the vision range is equal to 2, the alignment rule is able to have all workers in the network flock together at long time. However, for higher values of the vision depth, the gathering score decreases. This is because a worker can now see so far that he anticipates the arrival of other workers. In such condition, a small group aligned with a bigger in advance, its workers will turn back and be repelled by the bigger group before the two can merge. This results in a group of workers avoiding each other and therefore not gathering. We now run the same experiment as before, but with different vision depth for each criterion. Each cell on the figure displays a gathering score at the latest step of a run to see how different combinations of criteria play on flocking behavior. The y-axis represents the vision range for the alignment and the x-axis for the attraction. There is a lot to say there, and I put more details in the paper. But first, notice that the topmost line and the leftmost column correspond to the result we just presented. Now, on this figure there are 3 main results. The cell squared in red is a result we got in our previous work. The cell squared in green on the left is the best result from the previous experiment. Finally, the cell in green in the middle is the best result we get. Groups formed are almost 10 times bigger than our previous results. This combination takes advantage of the flocking behavior the alignment rules induces and of the gathering effect from the attraction rules. This gives rise to groups that flock while being able to move preferentially towards other groups. There's a last result I want to share with you. Remember all the social movement scenario? Well, it is crucial for protesters to form groups that resist adversary forces that may break them up. So let's have a look at the following experiment. We run a simulation for 500 steps, then we impose walkers to move completely at random for 1 step, as if they were all dispersed, broken up. Finally, walkers are allowed again to use once more their tactic until the end of the run. We performed this experiment with the alignment tactic and the vision-enhanced alignment tactic. On the figure, the x-axis is the time and the y-axis is the gathering score. At breakup both tactics, group size drop drastically. However, for walkers following a tactic with a wider vision, not only they are able to recover from the breakup, but they end up forming groups even bigger than before. This is thanks to the longer vision depths that allows the walkers to interact further and therefore to recover from the breakup. Thanks a lot for listening up to the end. If you have any question, you can directly email me or you can leave comments in the description below. I undertake to answer all of them. Goodbye.